He was an absolutely gorgeous baby, and we were so incredibly happy to finally hold him in our arms. He was diagnosed with one of the rarest immune deficiencies known as SCID. It meant he had no immune system, and we were told that he would not live to be a year old. Having a precise diagnosis allowed Fitz to qualify for a gene therapy clinical trial that could increase his chances for a normal life. During the entire process, he was always cheerful, and sometimes I would have to shake my head in disbelief of how amazing he was in light of everything that he was going through. He always had a sweet and happy temperament, loved to smile and flirt with his nurses. For Halloween, we went all out and dressed him in 5 different costumes.
Yes, we're here to make some music. Said we're here.
Fitz is the happiest toddler, always smiling and always laughing. It's as if he knows every day of his life is a gift. He's not only surviving, but thriving. We'll forever be grateful that he's benefiting from 2 of science's latest innovations, rapid whole genome sequencing and gene therapy. And now, he's got his whole life ahead of him.
Hello, I'm Stephen Kingsmore, and after that fantastic video, I'm going to talk about how newborn screening can be integrated with rapid whole genome sequencing, as you've just seen, for severe infant onset genetic diseases. I don't have a conflict of interest associated with this presentation. So Fitz is a fantastic example of how to integrate newborn screening and rapid whole genome sequencing. In this case, it's a T-cell receptor excision circle positive result, which informs the the idea of the possibility of SCID or another genetic cause of T lymphopenia. And rapid whole genome sequencing, like newborn screening, has very rapid turnaround time, and it provides confirmatory testing, diagnostic testing, for all of the conditions currently associated with TREC positivity, and they're listed below. So let's dig into this a little bit more and talk about rapid whole genome sequencing. So it's been made possible because of the rapid drop in the cost of genome sequencing, as you can see here, from about $18.5 million down to less than $1,000 over the last decade. What you might not be so familiar with is in the same time period, a rapid drop in turnaround time. So it used to be that genomes took months to sequence and interpret, and just this summer, a new benchmark was published of 13.5 hours, and I'm going to talk a little bit more about that. And against that backdrop is the rapidly increasing number of genetic therapy approvals, and that, of course, is tied to the recommended uniform screening panel for newborn screening. As an effective genetic therapy is approved, there then is a process of potentially moving that into the RUSP and needing to cover that condition as part of newborn screening. And I'm going to talk about how rapid whole genome sequencing will increasingly be looked at as a solution for this gap. So the number of known genetic diseases has increased very, very rapidly over the last several decades and now stands at 6,200 genetic diseases for which the molecular basis is known. And that number increases about one a day. What this means for critically ill kids is that there are very many conditions to be examined for many common presentations, and you can see some of those listed. Seizures, intellectual disability, recurrent infection. Literally thousands of genetic diseases need to be tested for to arrive at a molecular diagnosis. And the advantage of whole genome sequencing is that a single test can examine for them all. So it's kind of a universal test for genetic disease and replaces the idea of serial tests, either singleton gene tests or different gene panels and chromosomal microarrays. This technology has started to show us that hitherto we have missed very many genetic diseases in terms of their impact on morbidity and mortality in infants. This is unpublished work and looks at a series of several hundred infant deaths. And these are the causes of death in those infants, and they fit the national vital statistics. Then we decoded the genomes of each of these infants, mostly post-mortem, and found that the leading cause of infant mortality was actually genetic disease, and that many of these were not mentioned on death certificates. So as I said, the burden of genetic disease is much greater than we are currently detecting using conventional diagnostic modalities. So let me give you a case example. You've already had one of Fitz, of a baby who benefited first from newborn screening, then from rapid whole genome sequencing, and finally from an effective gene therapy. Let me give you a second case which did not start with newborn screening and didn't end with genetic therapy. This is a 5-week-old little boy who presented last year to our emergency department just before midnight on a Sunday. His mum reported that he had been crying inconsolably and been extremely irritable for a couple of hours. The doctor noticed evidence of encephalopathy, and also that his parents were consanguineous. They were actually first cousins. And so on that basis, he had a computed tomography scan of his brain, and the results are shown on the right. It's actually an MRI, not a CT. And A through C, the white lesions shown on those axial slices of the brain are abnormal. They look for all the world like hypoxic ischemic encephalopathy. That's not what this child had. There was no evidence, no history rather, of a hypoxic insult. And so he had a condition which was masquerading as HIE. So he was admitted to the intensive care unit in our hospital, and the following morning we obtained a detailed family history, and it turned out that his sister, 10 years earlier, had presented in an identical manner with identical findings on her brain MRI shown in panels D and E. And unfortunately, she had gone undiagnosed and died a year later of progressive encephalopathy. So obviously we were concerned that with consanguinity in this family history, that we were dealing with a recessive genetic cause of this child's symptoms. So in a couple of hours, we were able to get authorization for rapid whole genome sequencing. Parents provided consent. We obtained a blood sample and it was transferred to our genome sequencer, our genome center, where sample prep began. About an hour after sample prep started, we had the library on a genome sequencing device. This is the latest method for genome sequencing or rapid genome sequencing. As you can see, it's possible within about 13 and a half hours. And this is based on optimization of each of the steps in the protocol and a lot of automation. On the bottom of the slide, you can see the analytic performance of genome sequencing using these methods. And it has come a long way in the last decade, where now, certainly for nucleotide variants, precision and recall are wonderful. And even for structural and copy number variants, the precision and recall are better than any other method available today, and that includes chromosomal microarray. So the child's genome finished about 7:30 a.m. About 8 a.m., he was noted to be starting to have seizures on electroencephalogram. Unfortunately, we made a diagnosis using the methods I've just shown you. That diagnosis was autosomal recessive biotin thiamine responsive basal ganglia disease, and as the name indicates, this is a treatable disorder, and by giving high-dose biotin and thiamine supplementation, we can actually correct this if we diagnose it early enough. And so within 3 hours, and in fact that's 37 hours after symptom onset, he had his first doses administered through an NG tube, and amazingly by 6 p.m., his irritability had resolved, his encephalopathy symptoms had disappeared, he no longer was seizing, and he was feeding and tranquil and appeared like a normal baby. He remained in hospital for a couple of days for observation and to teach mum how to crush the biotin and thiamine tablets and administer those. And he's now about 8 months old and doing great. He's not been readmitted. He's had no further seizures. So rapid whole genome sequencing is an evolving method akin to newborn screening, that's really a healthcare delivery system, and today it has focused on critically ill infants and children in intensive care units. It has 4 elements. First of all is equipping of NICU teams, that's neonatal intensive care unit teams, to actually practice this, since it's not currently taught in medical schools or in residencies and fellowships. Then is the actual test piece, and then translation into optimized care. And lastly, increasingly, since these are genetic diseases, these results are informing the types of new genetic therapies that I showed you on a previous slide. It's now possible to develop a genetic therapy within about a year, and so we are seeing that rapid whole genome sequencing is now enabling an acceleration of genetic therapy development. So let's look at the evidence, the broader evidence beyond a couple of case reports that this is effective. And here is the INSIGHT study, which was funded by the National Institutes of Child Health and NHGRI, where we enrolled 213 infants in our intensive care units to receive rapid whole genome sequencing. The results are shown on the right. That about 21 to 46%, depending on the severity of illness, were diagnosed with a genetic disorder, and the vast majority, as we expected, had a change in management, and a minority, but a large minority, had a change in outcome, 39%. This study also looked at parental perceptions, since when we first developed this a decade ago, there were quite a few concerns, ethical concerns, in terms of whether parents could cope with genome sequencing for their critically ill newborn. And in fact, we found that there was really no basis for those concerns, that they just weren't observed in practice, as you can see on the parent line. Much to our surprise, we found that negative results also had clinical utility and also were felt beneficial by parents. And what we realized after the fact, as a result of these findings, was that a negative genome test had quite a bit of power to change the differential diagnosis. We had effectively decreased the likelihood of there being an underlying genetic condition, allowing physicians both to change therapies and to look for other diagnoses. And this is the complete world's literature at present related to diagnostic and clinical utility, both of rapid genome sequencing and of rapid exome sequencing. Some 24 studies are listed here, and the results are quite similar. A diagnostic rate of about 1 in 3, change in management at about 30%, and change in outcome at 25%. So on the basis of this, we have started to see implementation of genome sequencing in this population on a national scale. And this is one pilot study that's now published called Project Baby Bear, where the California legislature asked us to recapitulate what I've just shown you in Medicaid infants across California. And we enrolled about 180 babies, and their zip codes are shown on the right at 5 children's hospitals shown on the left. Overall, the findings were very similar to those that I showed you in the table. So 43% of babies received a genetic disease diagnosis. 31% had a change in management as a result, and time to result averaged 3 days. This study also asked us to look at the cost of implementing rapid whole genome sequencing in Medicaid infants. And we actually found that the cost was a negative value, that there were cost savings, largely resultant from decreased length of hospital stay. Remember, these were babies in intensive care units where a single day saved in terms of hospitalization results in thousands of dollars of cost savings. We did a sensitivity analysis and found that time to result determined the savings. This is just savings during that initial hospitalization. The total savings also include ongoing cost of care savings and family savings. And since this study was just completed about a year ago, those ongoing cost of care savings will continue to accrue with time. But overall, the net savings across the 180 or so babies was $3.7 million, or more or less about $20,000 per baby tested. As a result of this study, we now have approval of rapid whole genome sequencing by Medicaid in California. And then more recently, as a result of a sister project called Project Baby Deer in Michigan, there's also a Medicaid coverage policy in that state. In addition, Blue Cross Blue Shield provides coverage nationally for rapid whole genome sequencing in infants in ICUs. In addition to that, the National Health Service in Wales and England have adopted this as policy, and so has the Australian healthcare system. So we are gradually seeing adoption of rapid whole genome sequencing across much of the first world. So I want to finish up with talking a little bit more about integration with newborn screening. So rapid whole genome sequencing, as it's currently configured, is a diagnostic assay performed broadly on infants with symptoms who are in intensive care units. But we really wanted to look at whether it could be reconfigured with a screening modality in mind, thinking about conditions which are not currently on the RUSP. And so the first step in that was really using experts and artificial intelligence, using the phases shown here, to build a management guidance system to really identify every genetic condition which had onset in infancy and which could result in admission to an intensive care unit and for which effective treatment was available. And not just to look at whether effective treatment was available, but also to look at the evidence supporting that. And this is really somewhat similar to what happens at the Secretary's Advisory Panel as they consider whether or not a condition should be added to the RUSP. And to date, we have looked at about 350 conditions, although this slide was made a while ago. And in the first 150 conditions, you can see the number of publications that we reviewed and the various types of treatments that were considered to be effective in those conditions. As you can see, they cover all organ systems. They are weighted towards metabolic and neurologic conditions, but really every organ system is covered by these conditions. And interestingly, it's not just medications that are effective therapies. The therapies also include surgeries, dietary interventions, and devices. Here's one example, Timothy syndrome. This is a cause of sudden cardiac death and sudden infant death syndrome. So it's a ventricular dysrhythmia associated with a calcium channel gene. And this is the actual page from GTRX, the system that we've built to guide management of newly diagnosed babies with this disorder. You can see that there's an initial sort of red bar warning in terms of something to be aware of the moment a diagnosis is returned, and then the recommended acute treatments and interventions and the evidence supporting those and when they should be started during an admission. And this continues with second-line treatments and then with additional information about the condition, since many physicians will never have encountered this very rare diagnosis before in a patient that they're caring for. And so let me show you what that's informing. Really, we have started to build a prototype for newborn screening by whole genome sequencing. It's intended not to replace RUSP-driven NBS, which is shown in the bottom, but as in the case of Fitz, a screen positive by a whole genome sequencing test would be included in the information being made available to physicians receiving a screen positive RUSP result. And so we would envisage that this would be true for all RUSP conditions, that they would not be reported outside of the normal communication panel or methods. But for conditions which are not included on the RUSP, including the 505 diseases which are now contained in GTRX, that they would be an accessory means of newborn screening. They would obviously also require confirmatory testing. And the unique thing about this system, and something which is completely necessary in order for it to work beneficially and with minimal false positives, is for it to be self-learning and learning from each negative and positive variant result, building a database of those results and also of the confirmatory testing. So this is something that we are hopeful will pan out. It's still being prototyped. I don't yet really have data to show you, but we are pretty excited about its potential. And with the falling cost of genome sequencing, we anticipate that this could be delivered at a cost that is acceptable for newborn screening. And given the recent uptick in the number of approved genetic therapies for infant onset diseases, we think something like this is going to be necessary, or alternatively, the RUSP is going to have many additional gene by gene, additional molecular tests added to it. And we don't think that is supportable in the long run, and probably something like this makes eminent sense. So just to summarize, rapid whole genome sequencing is being implemented in infants in intensive care units to guide therapies in those infants. The indication is a child in an intensive care unit who at time of admission has a disorder of unknown etiology. The impact on outcomes is becoming very clear across over 20 studies. And in the future, we anticipate that what I've shown you will become more and more integrated with newborn screening, and that this is an optimal use of the technology. It's certainly not optimal to await a child being admitted with critical illness to an intensive care unit. And on the right are Riley and Sebastiana, two little girls who are now preschoolers, both of whom received rapid whole genome sequencing and had treatable genetic diseases, and whose lives were saved as a result of this technology. Lastly, I'd like to acknowledge all of the folk who contributed to this work and to our funding agencies. And at the top, Adeo Lumen ab Amicis Auxilium stands for to God for creativity and to friends for help. Thank you very much.